morning, class. Welcome to today's lesson. Today we are going to continue with our topic, input-output methods, but we are going to dive deeper. So you remember our last session, we discussed about different input-output methods, whereby we saw that we can interface microprocessor in different methods to the outside world. We have methods which are very simple, like input-output mapped, input-output, and then we have input methods which are very complex, like the handshake input output method. So we can either treat an input output device as a simple input output device, or we can treat that input output device as a memory. So if we treat an input output device as a simple device, then we assign those input output devices an address up to 256 bits. But when we interface an input output device as a memory, then we have to address it as a memory. And it means that we are going to use the memory address space, which goes up to 64 KB. Today we are going to focus on the input output device. A specific device which we are going to focus with is 8255. So welcome to the lecture. So in our today's discussions, we are going to do some introduction. Then we'll focus with why we need interfacing, or why is interfacing necessary. And then we are going to see role of peripheral devices in microprocessor systems. And here we are going to talk most about the 8255. Then we are going to recap on the 8085 bus architecture, which is not a new concept to you. And then we'll dive into Intel 8255. This is a programmable peripheral interface. It's a type of IC which we can program to interface other input-output devices with less complication. Actually, to interface all devices in this world, it's very difficult. And Intel saw this as an issue, and they decided to design their own chipset, which is 8255, which can be interfaced easily with 8085. Now, for you to understand this concept much better, let's assume that you are an African, maybe you are from Kenya, and you are traveling to China. So it means that for you to communicate properly with the people from China, you'll have to learn Chinese language, which will take you 2 years, at least maybe. So now, what is the another way around? Another way around is for you to go there and hire a translator. So this translator will be working with you in every street, in every place, so that you'll be speaking to the Chinese in English, and the Chinese will be speaking to you in Chinese. But the translator is the one who is going to do this heavy lifting of translating from one language to another. That's the same case of 8255. We don't need Intel 8085 to communicate to all devices in this world. We only need it to communicate to 8255. And then all devices in this world can communicate to 8255. So 8255 is the bridge between the Intel 8085 and any input-output device. And it is very easy to interface this way. So we are going to see much about that one. And then we are going to look at the addressing map of 8255. You will realize also 8255 has internal registers, 12-bit, to accomplish some tasks. We are going to see how to address that control register. And then we are going to look at the modes of operation. We have 3 modes of operation for the 8255. We have mode 1, which is for simple input-output device. We have mode 2, which is handshaking input-output. I mean mode 1, which is handshaking input-output, and then mode 2, which is bidirectional port A only. So we are only using port A to exchange data port B and C are going to handle the control signals. So we are going to see actually these ports. Don't worry, I've introduced the ports, so it's not, maybe it's not making sense, but I told you the port is the interface between your microprocessor and the outside world. And then we are going to look at the control word register. We see how to control these ports, how to control the chipset itself, that is 8255. We are going to see interfacing examples, the examples which we can use to see how Intel 8255 is the interface to Intel 8085. And then we are going to look at the advantages of 8255 in input-output interfacing. And then summary, we are going to look at lastly, we are going to look at the summary and some key takeaways. So I've said that microprocessor has a limitation of communicating to all devices in the world, especially these small devices like LEDs, keyboards. In truth, they cannot communicate to them. So we need now an 8255. That is an interfacing device. So in this introduction, we are being asked, why do we need interfacing input-output devices? And we are being told that the 8085 microprocessor communicates with the outside world through input-output devices, which is switches, LEDs, keyboards, sensors, display, etc. So since the microprocessor itself cannot directly drive or sense many devices, we use interfacing chips. So you cannot know all the languages in this world. So you will need what? A translator. And that's the reason why also Intel 8085 need 8255. That's an interfacing device. One of the most common and versatile chips is the Intel 8255. This is a programmable peripheral interface device. And we are going to look at this device. We have diagram here. So this is a pinout diagram. You see we have a total of 40 pins. Yes, we have a total of 40 pins. So we have all these pins have been categorized to either we have a total of 40 pins. 24 of these pins are for carrying data, and these 24 pins have been grouped into 3 groups, which makes 3 ports. So we have a port which can carry an 8-bit data. So if we combine a total of 3 ports, we are able to carry up to 24-bit data. But that is not possible because these ports are used for different purposes. We are going to see sometimes you cannot use all of them to transfer data. Sometimes you have to use one port to do the control of the data transfer, and then the other port will be transferring the data. We are going to see that in details. But to take you just through them, we have all these pins you see starting with PA, PA, PA. Those are connected in port A. Those are pins which are connected to port A. And all those you see which contains PC, 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 those are pins which are connected to port C. And then we have some PB, PB, PB. Yeah, those are port pins connected to port B. So we have a total of 3 ports: port A, port B, port C. We are going to see how they are used. And then we have control signals. We have RD. We have chip select signal. We have again WR. We have reset. Those are control signals, and we are going to see how to interface them to the Intel 8085. And then we have power pins. That is pin number 7, ground. And then we have another pin for power. Have you seen where is another pin for power? So it should be labeled something like VCC. this one. It is pin number 28. I think so. It's pin number 26. That is for the power. So let us now look at the inside of the Intel 8255, the architecture of the IC, how it has been designed. So as you see, let us start from this left side. So when you want to exchange data between the Intel 8255 and our main microprocessor, which is Intel 8085, then we need to interface our data bus of Intel 8085 to this data bus of the 8255. So we do understand that Intel 8085 can carry an 8-bit data at a time, because the data bus with it we have only a total of what, 8 lines in the data bus. So 8 wires in the data bus. Each line or each wire can carry a bit. So when we do what is called parallel transmission, we can carry a total of 8 bit at a time. And that's how we say it's an 8-bit microprocessor. So those 8 lines of the data bus are connected to D0 to D7. So that's how we are going to exchange data between our 8255 and our Intel 8085. And then the control signals from the Intel 8085 are going to be interfaced to this read/write control logic. So we see we have RD, we have WR, we have A0, we have A1, we have reset, and then we have chip select. You know the work of RD and WR. When the microprocessor is going to send data to 8255, it's going to activate this signal WR. That data is going to be written to the 8255. And if I want to read data, or if the 8255 wants to exchange data with wants to send data to Intel 8085, then we are going to activate this signal RD. By activating this signal RD, the Intel 8085 will be able to read data from 8255. The work of A0 and A1 is to select which port we are going to use. If all of these are 00, then there's no port which have been selected. And then we can select one of the ports by either changing from 01, 10, or 11. So we are going to see more about that. Reset is to reset the chipset to its default. It means that all the data which are inside here are going to be to be lost. Also, it means that the ports which we've selected to exchange data with are also going to be reset. We are going to see how we configure these ports. And then we have the chip select. Chip select is to enable this IC to be active or to be inactive. If we want to activate this IC, then we have to drive this pin low. And I think I have to talk about this. You remember I told you that when you see a signal with a dash above it, it means that that signal will always be activated if you drive that pin low. When you drive this pin low, then you activate that pin. So for example, if I want to read data from the 8255, then the microprocessor will write this pin low. It will drive this pin low, and then we are going to read data. If I want to write data to the Intel 8255 from the microprocessor, then microprocessor will drive WR signal low. If I want to enable this IC, that is 8255, then this chip select signal will be driven low. when you drive this signal low, then the chipset will be activated. And then let us come. I told you that the 24 pins of Intel 8255 have been categorized into 3 ports. So we have port A, which is PA0 to PA7. We have port group A, port C upper. So we have port C upper, and then we have port C lower. So port C upper is from PC4 to PC7. Yes. And then port C lower is from PC0 to PC3. And then we have port B, which is PB0 to PB7. What I want you to understand is that port A and port B, they contain a total of what? 8 pins each. But apart from that one, they contain extra pins, 4 each pins. So we have port A, which contains an extra 4 pins, and then we have port B, which contains what? An extra 4 pins. The extra 4 pins from port A, they will create port C, but upper pins. The extra pins in port B is going to, extra pins in group B is going to form part of the pins in port C, but these pins are going to occupy the lower part. I think this is just designed to utilize the IC well, and to make sure that we don't have a lot of excess pins. Yeah, I think that is the reason why they did that. Now, for us to understand how to interface our 8255 to our Intel 885, it is very important for us to recap on the bus structure of the 885. Remember that 885 contains also 40 pins. Yeah, in these pins we have pins for different purposes. We have pins for controls, we have pins for address, to carry addresses, we have pins to carry data. Pins which carry control signals are grouped together, and we call them what? Control bus. Pins which carry the address, we combine them, we group them and call them what? Address bus. And then the pins which carry data, we group them and we name them what? Data bus. So we have the address bus, we have the data bus, and we have the control bus. The address bus is from A0 to A15. This identifies whether CPU is addressing memory or input-output device. So we know these buses, or this address bus, is going to carry addresses for whether these addresses are for input-output devices or whether these addresses are for the memory. So we are going to carry all these addresses. And then we have the data bus. It's a total of 8 pins. It's from D0 to D7, transfer data from the input-output devices and the memory. And then we have the control bus. These are for carrying control signals. We have the RD, is one of the control pin. This is for read operation. Then we have WR. This is for write operations. And then we have input-output stroke M. It differentiates whether the transfer the transfer process is for input-output devices or from the memory. And you remember I told you, if this pin is driven high, if we drive this pin high, then the exchange of data is going to happen between input-output device. If I drive this pin low, then the exchange of data is going to happen between what? Intel 885 and what? And the memory. So with these signals, the 885 can talk to peripheral chips like 8255. So it means that the Intel 885, it's going to treat 8255 as a memory input-output device. It's very important you understand that. But of course, the 8255 is going to give us other input methods. Despite we are treating it as a memory input output device, it's going to allow us to interface using other input output methods, and we are going to see that one under modes of operation. So I have provided here a simple diagram. This is figure 3. This is a simple diagram showing how we can interface our Intel 885 with Intel 8255. So 8255 is a programmable input-output device that acts as an interface between peripheral devices and the microprocessor for parallel data transfer. 8255 PPI is programmed in a way so as to have transfer of data in different conditions according to the need of the system. And we are going to see these different conditions. And I've said that one we are going to discuss them under modes. So we can have mode 0, mode 1, or mode 2. A total of 3 modes of operation. But that one is going to come later. But this diagram actually gives you now a real picture which I want you to be seeing until we finish this session. So we have our Intel 885, which is our microprocessor. We've said this microprocessor is not able to communicate to the input-output devices directly because it cannot have that mechanism. Even if we add that mechanism to the Intel 885, we are going to complicate the issue. It's like having your child and you want your child to learn all these languages before actually maybe starting a school. I'm telling you, he's going to start school maybe when he's 40 years old. So now a lot of complication is not necessary if we can design another IC to handle those complexity. So, and that's why the reason why we have Intel 8255. So the main transfer of data is going to occur in the data bus. We have an 8-bit data bus, and this is bidirectional. And then we have the control signal which is unidirectional. We have RD, WR, A0, A1, reset, and CS. I told you that RD, WR is for reading data or writing data to the Intel 8255. A0 and A1 is for selecting which port we are going to use. Reset is for resetting the operations of the Intel 8255, including the configuration we've made. Chip select is for activating this IC. And then now, in turn, the Intel 8255 is going to communicate with the outside world using the 3 ports: port A, port B, and port C. And we are going to see how is that possible. So as we've discussed, Intel 8255 is a general purpose programmable input-output device. It means that it can do any handling between the input-output devices and the Intel 885. It provides a 24 pins for input-output operation. And that's why they say it provides 24 input-output lines, which are grouped into what? 8-bit ports. So we have port A, which is 8 bits from PA0 to PA7. Port B, 8 bits again, PB0 to PB7. And then we have port C, which is PC0 to PC7. But this one, port C, we've seen it has been split into 4-bit groups. And we have the upper, which is in group A, and we have the lower, which is in what? Group B. And maybe you are going to see why are they doing that. Can be programmed to work in different modes to suit various input-output needs. You are going to see those modes. We've said we have mode 0, we have mode 1, and then we have mode 2. So pinout and functional blocks. So we have the data bus. Our data bus, which we are going to use to exchange data between the 8255 and 8085, are D0 to D7, a total of what? 8 bits. This one connected to 885 data bus. And then we have the address lines only two address lines, that is A0 and A1. Select one of the ports or the control register. Then we have RD, WR and CS. These are write and chip select. Then we have reset, clears control register, all ports default to input. So sometimes we are going to see how to configure these ports, and if you want to reset them, you can reset them to default. If you reset them to default, they are going to be default to input ports. They are going to work as input, no, not an output. So if you want to configure the port to be an output, there's a way we configure them using what? A0 and A1. Those are the two pins which we use to configure what? The Intel 8255. Now, this is a very important section for us to understand how to configure these 8255. By us understanding the addressing mapping, we are able to configure this 8255. Remember, configuration of 8255 will always happen through the software. So you write a code. Part of the code, when you do programming, part of the codes which you are going to develop, if you want to interface an input-output device like a keyboard or an LED, is for you to configure what? To configure the 8255. And we are going to see which are these special instructions which we can use to configure 8255. So the address mapping for the Intel 8255 is determined by the two least significant address lines, that is A0 and A1, in conjunction with the chip select signal, which is CS signal. When the chip's select signal is low, that is active low, so I told you that we have to drive it low, the 8255 is enabled. The combination of A1 and A0 address lines then selects one of the four internal registers for the 8255. So we have to select one of the four internal registers using what? A1 or A1 and A0. But remember, before you do that, you have to enable the chipset. How do you enable the chipset? The microcontroller is going to drive this CS pin low. The microprocessor is going to drive this CS pin low. By driving this CS pin low, then the chipset is going to be activated. So then how do we do port selection? So I have a summarized table here if you want to do port selection. So which port are you going to use? Are you going to use 3 of them? Are you going to use 1? Which one is going to be the input? Which one is going to be an output? Plus other information. So if I send 0 and 0, 0, 0 to A1 and A0, if I'm going to send a 0 bit, then port A is going to be selected. If I'm going to send 0, 1, then port B is going to be selected. If I'm going to send 1, 0, then port C is going to be selected. If I'm going to send 1, 1, then control word register is going to be selected. So these are different registers. We have register for port A, we have register for port B, we have register for port C, and then we have the control word register. A total of 4 registers to be selected using what? A0 and A1 address lines. Address mapping example. For example, we have a simple example here. So if I send this an hexadecimal data, you see it sending with 1. So if I'm going to send 00H, which is an hexadecimal number, equivalent again to 00 as a decimal number, then port A is going to be selected. If I send 01, port B, 02, port C, then 03, control register. And then let's say if After selecting which port register I want, then from there I can follow up with these instructions. So we have the in instruction. This is to read data from the port A. So if I'm going to say in 00H, then I'm going to read data from the register 00H, and this register is connected to what? Port A. And if I'm going to use this instruction out, these are just some simple example. So out 01H. So I'm sending data, or I'm writing data to register which is connected to what? Port B. If I'm going to write out, the instruction out 03H, I'm sending data, or I'm writing data to the register which is connected to what? Which is connected to control word register. Yes, this for configuration purposes. So we've said in 00H, it's reading data from port A, and if I say out 00H, out 00H, then I will be writing data to port A, and we can exchange these instructions accordingly. So let's say if I wanted to read data from port C, then itakuwa ni in 02H, in 02H. So this is when I want what? To read data from what? Port C. I think that's a good example. So we can continue. So I think it's time now to focus with the modes of operation. I told you that 8255 has 3 modes of operation. So we have mode 0, mode 1, and mode 2. So in mode 0, this is when we want this 8255 to act like a basic input-output device. Basic input-output basic input-output interfacing device. What does this mean? It means that this Intel 8255 can able to communicate with what? Simple things like LEDs, keypads, yeah, if we use this mode of operation. And then we are going to see other modes of operation and where can we use it. So let us start with mode 0. So this is the basic mode of simple input-output operation. In this mode, each of the 3 ports, that is port A, port B, and port C, can be independently configured as either an input or an output port. This mode doesn't support handshaking or interrupt capabilities. It is good for LEDs and also what? Switches. These are switches which will give you 2 state, either on or off. Sana vitu kama push button is a good example. And then we have mode 1. This is for strobe input output with handshaking. This mode provides handshaking signals for input output operations, making it suitable for transferring data to or from a peripheral device at a speed that is not synchronized with the CPU. So port A and port B can be configured in this mode. Part of port C is used for handshaking signals such as STB, that is strobe, and IBF, input buffer full. So we are seeing in this mode, which is mode 1, we can use the 8255 to exchange data between input-output devices and our CPU. But the speed is not going to be synchronized. Port C cannot be used to transfer data. Only port A and port B. So here port C can be used to do handshaking signals, and you've seen how that is done. And then we have mode 2. This is bidirectional only. Only port A can be used in this section. So if you want to use mode 2, only port A is used. Mode 1, port A and B is used. Mode 0, all the ports are used. So let's see about mode 2. Yeah. So mode 2, if you see mode 2, this mode is available for port A only and allows it to be used for bidirectional data transfer. Port A can both transmit and receive data with handshaking signal provided by port C. This mode is useful for communicating with devices like disk drives. Very high speed exchange of what? Data. That's why I say this 8255 is a very important interfacing device. Can you imagine we can interface simple things like LEDs and switches to complex devices like disk drives? And you can program it to either do this or this one. And we've seen as you go down, you reduce the number of ports because you need port C to do the control structure, the control of data transfer or handshaking. You also need port B to do other things, and that's why when it comes to mode 2, you only use what? Port A. But you can use this port A as either input or output bidirectional. So at any given time, it's going to exchange data out of the microcomputer environment or to the microcomputer environment. Now all these are going to be made possible if we are going to configure this 8255. There's no way you can say that port A equal input ama bidirectional ama tuseme you want to use mode 0, mode 1, yeah, mode 2. The only way you can use those modes, you have to configure this 8255. And how do we configure it? This 8255, apart from having 3 other registers for the individual ports, we have a special register for the control word register. It's called control word register. Now, control word register is a crucial component of 8255. It is a write-only register that is used to configure the operating modes and the input-output directions of the 3 ports A, B, and C. The format of the control word is a single 8-bit byte that is written to the register. The most significant bit, that is D7, determines the mode of operation. So if we are setting D7 to be 1, then input-output mode, this is input-output mode. This is used to program the ports to be either input or output in mode 0, mode 1, or mode 2. The other bits in the control word define the specific configuration, e.g. input/output for each port and the mode for each group. If I'm going to set D7 to 0 bit, then bit set or reset, that we use this one for the bit set reset mode. This mode is used exclusively to set or reset individual bits of port C. The other bits in the control word specify which bits to modify and whether to set it to 1 or reset it to 0. So to configure port, we write an 8-bit control word to the control register. So to make you understand this, we have a very important register which we say this is a control register. This register can carry a total of a byte. 1 byte is equivalent to 1 word, and that's why you see they are saying word register, because it can carry only 8-bit. This register we can only write data to this register, but we cannot read the data from the register. So if you want to write the data to this register, that data must be an 8-bit. For example, we have the least significant being D0 and the most significant bit being D7. So if I'm going to set D7 to 1, then automatically the 8255 is going to avail all its ports, that is port A, B and C, as input output ports. And if I set this pin to be 0, then I am going to make this 8255 to be in another mode of operation. And in this mode is used exclusively to set or reset individual bits of port C. So if I want to set or reset individual pins of port C, then I have to start with the D7 being what? 0 bit. So that's a simple example. We are going to see more as we advance. So we have an example of control word, and the control word is an 8-bit instruction written to control register of 8255 to define how each port will behave, whether input or output, which mode, and etc. The control register is selected when, how do we select the control register? Do we remember kwa hiyo summary yetu? We set A0 to be 1 and A1 to be 1 kwa address lines combination. Once a control word is written, the ports operate according to that configuration until another control word is loaded or a reset occurs. You see, all the time the microprocessor is going to send data to the Intel 8255, and that data is going to go to one of the registers. We have a total of 4 registers. So we've seen the data which we can exchange at any given time is an 8-bit what? Data. So that 8-bit data can go to one of the registers. Now if you want that data to go to port A, then A0 and A1 should be 00. If you want that data to go to port B, it is 01. If you want that data to go to port C, then it will be 10. But if you want that data to go to the control register, then you have to set these address lines to be A1 to be 1 and A0 to be what? To be 1. And by doing so, any data which is going to be placed at the data bus is going to go directly to the control register. So we've said if I'm sending an 8-bit to the control register, those bits are going to do different configuration to the what? To the 8255. And one of the examples we saw is, for example, if I send 00000001, then automatically I've configured this 8255 to be what? To be input output mode for all the 3 ports. And if I do the other way around, we see you can have different what? Configuration. So let us look at the control word. This is a control word. Why are we saying it's a word? Because it's a byte. 1 byte is equivalent to a word. Now, why do we say it's a control word? It's a control word because anything you are going to put here, it's going to control what? The register. So we have D0 for port. So D0 is going to be for what? Port C lower. D1 is going to be for port B. D2 is going to be for group B. D3 is going to be for port C upper. D4 is going to be what? For port A. D5 is going to be for group A. D6 again is going to be for group A. And then D7 is going to be this, where we say it either 1 or 0. So if we set it to 0, then it means that we are trying to configure port C. If we set it to 1, then we've configured all these ports to be either input output ports. So D7 is equals to 1 indicates this is a control word for input output mode. So group A need D6, D5 na D4. Control port A and upper half of port what? C. And then group B is D2, D1, D0. Controls port B and the lower half of port C. then we have port C upper, and then port C lower. So for port C upper ni PC4 to PC7, then port C lower is from PC0 to PC3. So we have an example here, two examples here. Let's say I want to send this data, which is an 8-bit binary. So we have bit indicating this an 8-bit binary number, which is equivalent to this hexadecimal number. So if I'm going to send 00001001, so this 0 is going to be our D0, and this one is going to be our D7. This one is equivalent to 90H. So if I'm going to send 90H as hexadecimal number, it will do the same configuration. So we've seen already that this is a breakdown. So D1 is equals to 1. It means that this is input-output control word. So by making it to be 1, we are setting the ports to be either input or output. Then from there, we are seeing D6 and D5 zote zimekuwa 0 0. So 0 0. This one is mode 0 for group A. D4 tumeweka ikuwe 1. This is for port A input. We are setting port A equal input. D3 tumeweka ikuwe 0. Port C upper is equals to output. D2 ni 0. Mode 0 for group B. This way up to down. So you should be able to follow up these examples later on. So what is being achieved here? Something which is being achieved here is that the results is going to be port A itakuwa input, port B itakuwa output, and then port C itakuwa, which is both upper and lower, it is going to be our output. Which mode can we use this for? It's good for connecting switches to port A and LEDs to port what? B and C. Another example, if I'm going to send this data 01000001 as a binary, which is equivalent to 82 in hexadecimal, it's going to achieve this again. So if you follow up, if bit D7 is 1, we do understand that is for input output. 0 0, this is the same as here, so mode 0 for group A. Again, all the things are going to maintain apart from this part. So D1, here D1 was 0, here D1 is 1, so it means that port B is input. So if you want to set a port to be output, then the bit for that port should be 0. If you want to set a port to be input, then a bit for that port is going to be 1. So for example, if I set 1 here, then port C, the lower part is going to be input. But they have set it to 0, it means it's going to remain as an output. So what is the results here? Port A remain output, port B is going to be input. Yes, as we've seen here. Port C is going to be an output. Yeah. All ports in the mode 0. So we've configured all ports to be in mode 0. Usage, we cannot connect LEDs to port A, switches to port B, and use port C to drive additional devices. We have an example here of how do we load now. You've seen these are how we are going to configure the port. But how do we load? How do we transfer this data? Iende kwa 8255, specifically to the control register. So loading the control word, in both cases the control word is sent to the control register. Now our control register, it's found in what? Address 03H. Don't forget that. You remember 00 is for port A, 01 for port B, 10 for port C, and then 11 for port for control register, 11 for control register. So 11 in binary is equivalent to 03 in hexadecimal. So anytime which I want to configure the control register, I have to make sure that I'm sending data to what? To this address. So first of all, I'm loading immediately. You remember MVI is an instruction to load data which it's not stored anywhere. It's not stored in memory, it's not stored in register. You have that data in your mind. So you want to transfer that data straight to the accumulator. Then you use this instruction. So MVI A 90H. So 90H, which is equivalent to this, is going to be stored to the accumulator. And then out. So I'm sending this data, which is 90H, out from the accumulator to 03H, which is what? An address. And this address is an address for input-output device, specifically for the control register of 8255. Yeah, that is for example 1. What about example 2? I will do the same thing again. MVIA, so I'm loading 82H, this is hexadecimal number, to the port to the accumulator, and then I'm sending that data from the accumulator to the address 03H, which is going to load into control register. After this, the 8255 ports are ready, and subsequent in or out instructions will behave according to this setup. So let us look at different examples. Example of applications we can do with our 8255. So in an example number 1 is when we want to interface what? A simple switch as an input. So example 1, when we want to use a switch as an input, but it is connected to port A. So the control word configuration for port A as an input. So first of all, we are going to read switch values with, now this is the instruction, in 00H. In is going to read data from this address. This address is an address for register which is connected to what? Port A. So if I'm reading anything in this address, I'm going to read anything from what? Port A. And then I'm going to store that results to memory location 2050H, and then I'm going to stop the instruction or the program. So let's say if I want to send a control word, if I want to let's say I've connected LEDs as an output device on port B, and I want to send a data which is going to turn on LED. So display pattern on LEDs. So MVIA, so I'm loading this data 0FFH. This is going to turn all LEDs on in port what? In port A. In port B, I mean. So it means that 0FFH, if you convert this into binary, you will be able to understand what does it accomplish. So I'm going to load this data to what? To the accumulator. And then I'm going to send that data from the accumulator to an address of a memory location 01H. And we do understand this address 01H is for what? Port B. So anything which is connected to port B is going to be controlled with this data. And then I'm going to stop the program. What about when it comes to keypad on port A? I'm a 7-segment display on port B. So port A scans keypad, port B drives display. Requires programming logic for scanning and display conversion. So up to that level, you now understand how 8255 is very important. By the way, this device is very, very important. We can use one IC to interface many devices. These devices can either be very simple, like LEDs, or they can be very complex, like USB drives. and that's the reason why we need that 8255. So apart from that one, 8255 gives us what? Flexibility, because all configuration are going to happen in software level. It's just writing the codes for configuration. There's no need for you again to do desoldering. You solder, you connect these pins. No, that one is not necessary. When you config, after designing your hardware, the next phase is going to be what? Software. And whatever device you are connecting to your microcomputer environment, you will be controlling them in terms of what? Software. So flexibility is very important. Another thing, it saves us the hardware complexity compared to using latches and buffers. When we are using latches and buffers to exchange data, our hardware becomes very complex because we are going to use several ICs to do different things. And that's why we say it saves hardware complexity, because by having only one IC, you can be able to do several things. Now, you have to understand this is widely used in teaching and early microprocessor systems. For you to understand how the modern microprocessor work, you have to understand how the old microprocessor used to function. And this is a good example for you to understand how do we interface things like keyboard, how do we interface things like LEDs, how do we interface things like keypads, mouse to our what? To our microprocessor. This is a foundation for understanding peripheral interfacing in modern microcontroller units. That is true, and I've said that for you to understand what is happening currently to the world, we have to go back in time. So those are the reason why we need what? 8255. But the most two reason is the flexibility and how it saves us the complexity of the hardware design. Now we've come to the end of our discussion, and as there are some key takeaways I want you to have with you. Number one, 8085 access external devices via input-output ports. I told you that one. 8255 provides programmable 24-bit input-output. So 8255 provides these input-output ports, and we've seen it contains a total of 24-bit, which has been grouped into 3 ports. Each port is going to be 8-bit. Ports are controlled using in, out, and control words. We can either send data to the port using the out instruction. We can read data from the port using the in instruction. We can even control what? The word register. Practical devices such as switches, LEDs, keypads, display can easily interface. So we can easily interface these input-output devices to 8255, which in turn is going to interface to what? To our Intel 8085. And I have the block diagram for you here to actually see again what is happening inside this IC. We've seen we have power, we have D0 to D7 to exchange data between our Intel 8255 and our microprocessor. We have the control pins, which are going to be interfaced to our Intel 8085 for control signals, and we've seen the work of all these pins. And then we have our ports which are connected to the outside world. We have a total of what? 3 ports. One port is port A, another port is port B. Then port C has been divided into upper and lower, as we've discussed. So this comes to the end of the question of the session of what we've discussed today. This marks also the end of this topic of input-output methods. Remember this topic, we have a topic which is called input-output methods or technique, and then we have another topic called input-output interfacing devices, input-output devices. So the part A of this session, which we tackled it last week, was actually focusing with input-output techniques. Part B of this lesson, it is touching input-output techniques and also what we are going to discuss in input-output devices. Remember here, we've not talked about how we interface things like what? Our keyboard. How we interface things like LEDs. We have a topic specifically for that, and we are going to continue with some of these tasks when we reach in that topic. I did not want to combine these two topics because if I combine them, first of all, they become too long and they become with too much information, which is going actually to complicate learning. I saw this with one of the classes. I combined this topic, and these topics were very, very big, and they were telling me, teacher, why are we learning the same thing almost 1 month? Is because they never knew that we were tackling input-output methods and also input-output devices. So I've decided to do an hybrid. We tackle the input-output methods. We bring in a very important device which is going to help us to discuss input-output devices when we get there. Thank you so much. Make sure you watch this video. Most of you guys don't watch the videos which I prepare for you. Remember, we are using this time to cover what maybe we could not be able to cover in class because maybe you are not around or something is coming up. And it's very important for us to have these online sessions, which is called blended learning. It's a combination of a physical learning and an online learning. For example, last week, you guys were not there, and actually we used this session to cover the lesson which maybe you could not hatungeweza kupatana. So make sure you watch this video. It's very, very important for you to understand how to interface our microprocessor Intel 885 to the outside world. Thank you so much. Have a good day. We'll see each other on Friday. Thank you so much.